Good afternoon, ladies and gentlemen. It's a great pleasure for me to be here. Stockholm Precision Tools has been manufacturing high-end survey tools for the mining business for over 25 years. Today I'm going to discuss how small survey error margins can have a big impact on value to your operations. We'll focus on the high-end exploration boreholes. Why do we need to survey boreholes? For mine feasibility studies, future planning, safety, and because no borehole is ever straight. And you cannot predict deflection of boreholes due to formation effects. At least you can't predict them predictably. So, currently available 3 types of survey tools. All of these tools are solid state with wireless communication to a handheld device for data integrity. All have multiple QC checks built into the software. Let's discuss the characteristics and then their weaknesses. So, magnetic survey tools use magnetometers and accelerometers, use magnetic north as the direction reference, and take stationary surveys. Reference gyros use accelerometers and/or gyros for direction change measurement. They need an input start direction reference to geographic north, measure continuously in all orientations, and are compact and light and ideally suited to short blast hole surveys. North-seeking gyros use higher quality gyros and accelerometers, measure absolute north, gyro compass to obtain a start direction or for multi-shot surveys, but also use continuous mode and can record thousands of survey data points per minute, and have no input of declination, correction, or reference direction required. And the errors associated with the different tools, magnetic tools, declination correction. In the oil and gas industry, they did a survey and found that the average declination was 0.3 degrees out. Doesn't sound like much, but it's significant. Becomes a systematic error if it's incorrect. And magnetic interference. If you have a very low level of magnetic interference, you're probably not going to see it. Even if your magnetic survey tool is very accurately calibrated, you still may not see it. If the magnetic interference is high, of course, then you have to discard the survey. No way to correct. So reference gyros generally use lower accuracy sensors than north-seeking gyros. Drift rates and corrections are larger and not as robust as for north-seeking gyros. There is also some level of error between the reference direction measurement and the input to the survey tool. This can be minimized. This can be minimized by using a matched north-seeking gyro-based rig alignment system, but never completely eliminated. So then we move on to north-seeking gyros. So they have a lower level of error due to using higher quality components. A gyro for north-seeking is obviously of a higher quality than a gyro for reference use. So drift checks take care of most residual drift errors. I think one of the key things about north-seeking gyros is the running speed. So tools with a higher measurement frequency, and they all measure at different frequencies, create more data. You can therefore run at a higher running speed for the same data density. So more data equals better surveys. So other error sources, survey misalignments. There are generally 3 potential areas for survey misalignment. Internal tool sensor misalignments, which are usually taken care of by multi-step calibration procedures in the workshop, and tool misalignment processing during the survey. And then we have external misalignments, centralization of the tool in the drill rods. This is reduced by using good centralization and low survey tool mass. And finally, centralization of drill rods in the borehole. This is not easily removed. Okay, so to get a survey, we need a measured depth, inclination, and azimuth. So we need to measure depth just as accurately as we measure dip and direction. Manual calculation of depth by calculating the number of drill rods, which is what you do occasionally for single-shot surveys, is not sufficient for a final survey. And obviously, if you've got a continuous gyro, you've got to have some kind of continuous depth measurement. So we need to use a depth encoder on the rig line or on a winch. And it's important to accurately calibrate the encoder on the rig line. This is a one-time operation. And we then expect a 1 to 1,000 depth accuracy. So we need both accuracy and precision from our surveys. And to survey accurately, accuracy is the difference between a measured value and the true value, whereas precision or repeatability is the consistency of repeated measurement relative to each other. So data can be low precision but accurate, high precision but low accuracy, and hopefully high precision and accuracy. And of course, it can be none of the above if you're unfortunate. So repeatability of the data is actually just as important as the accuracy of the tool. Your mine surveyors work to 3 sigma, or 99.7% precision. You survey your mines and collars to millimeter accuracy. We need to be in step and use the same precision to compare tool accuracies. So basically, why would you throw away that carefully built accuracy when it comes to borehole surveying? So what's the issue? Why are we mentioning this? Well, different manufacturers quote their accuracies to different levels of certainty. Most manufacturers quote to sigma 1, which is 68% certainty. Others quote to sigma 3, which is 99.7% certainty. That's a big difference. If you quote to 68%, you're effectively saying that there's a 32% chance that the survey might be outside the area you're specifying. So, if you want to convert accuracies, published accuracies to 1 sigma to 3 sigma, just multiply by 3. It's as simple as that. So what have we done here? We've got ellipses at this point of uncertainty. So in this case, you can see that the red circle is 1 sigma, the black circle is 3 sigma. So as I say, we can end up with a situation where we're saying we're this accurate, but in fact, we could be outside that area. So ellipses of uncertainty, or ellipsoids of uncertainty, the 3D version, are cumulative, which means that each ellipse is going to get larger as you go further down the borehole. We think we should be using 99.7% certainty. It guarantees catching any possibilities of surveys being outside of the ellipse. And of course, if you use a more accurate survey tool, you will end up with smaller ellipses. So how do we get from a measured depth, inclination, azimuth to borehole coordinates? We need to use some kind of calculation method. So here you can see, in increasing order, an evolution of calculation methods used. And minimum curvature is the current standard, the most accurate of all of these. However, it's still an interpolation of survey points between those two surveys, whether as a straight line or as a curve. So here we're going to just discuss this a bit further, and we have just a diagram that shows you surveys taken on a 5 meter basis against surveys taken on a 1 meter basis. Green points are good surveys, red points is a survey error. Okay, I think you can see that intuitively a 5 meter propagation of an error is going to create more displacement error than a 1 meter propagation of that error and back onto the true track. The other aspect is, as I said, that if you're interpolating between survey points, you can be missing all sorts of bends and kinks in the borehole. So therefore, surveying on a smaller interval is better than surveying on a longer interval. And by extension, if we go over to continuous surveying, where you're surveying thousands of points every minute, down to centimeter level, you're going to have a significantly better calculation of borehole position. Okay, so when you've got your full survey, we strongly recommend that instead of just surveying one way, you survey in and out of the hole, make an in-run and an out-run. Each survey then can be independently calculated, and we can compare the data at the bottom of the hole, or anywhere you like along the borehole path, and calculate the lateral and vertical difference in depth. Vertical difference in depth and lateral horizontal difference in position between the two surveys. So in this case, the TVD difference, the true vertical depth difference between the two surveys is less than 1 meter per 1,000 meters, and it passes specification. The lateral differences are greater than 1 meter and fail. So this survey would have failed that test. It's a great check on repeatability of your data. Okay, so we've taken published tool accuracies for commonly used north-seeking gyros and calculated the associated displacement errors for an example borehole. You can't see that very well, I don't think, but so the borehole is 500 meters long and dipping at minus 60 degrees. So on the left of the chart, we've got 5 different tool accuracy levels. We've done this for azimuth and for inclination. So we've got error margins A, B, C, D, E. And these are from published specifications of different tools. In this case, we've been quoted as 1 sigma, and here we're quoting at 3 sigma. We've converted the 1 sigma to 3 sigma so that we can work in these green columns at 3 sigma accuracy levels. So then for that particular borehole, we've calculated the accuracy, the displacement at 500 meters for that survey. As you can see, azimuth accuracies are much lower than inclination accuracies. I'm sure that's not a surprise to you. So here, between the most accurate inclination and the 3rd level, or the 3rd tool example, we can see we have a 0.44 meter accuracy and a 3.93 meter accuracy. So we've got 3.5 meters difference. We'll apply that later in a minute. Okay, so here's our example borehole. Here's our formation. Our example formation has a 1,500 meter strike length. It dips at 70 degrees. We don't know how far it extends. We've drilled a survey to 500 meters, hoping to intercept the ore body. And the blue is the error margin for this example. So if we combine that error margin with the intercept angle, we can calculate the true vertical thickness error that we may encounter at this point. Okay, so for this body, dipping at 70 degrees, 1,500 meters strike length, down dip distance 500 meters to the borehole. I've put in some rock densities and ore concentrations and metal values for gold, just to try to make some kind of valuation. Obviously, this is a very simplified model, but it's about the only way we can get some kind of valuation that sort of makes sense. So we've calculated the true vertical thickness for the ore body for each of the potential errors, and this is all for inclination, not for azimuth. Inclination errors are much smaller, so if you're drilling and trying to hit the ore body perpendicular to strike, then hopefully your azimuth errors are not going to be great, or as minimized as possible. So we'll stick to the inclination. So we've calculated true vertical thicknesses, volumes, tonnage, and values. So from tool A to tool C, we're going from 344 million to $3 billion value of that thickness of ore. So the difference in accuracy is worth over $2.5 billion. I hope that makes people think a little bit. Although you may think this is unrealistic, remember your ore body is not usually regularly shaped. So if you're drilling through a curved or around a curved body, the azimuth is going to come into play, and the azimuth errors are much, much greater. And this has been done, the azimuth errors that I did previously were calculated for a continuous survey. When you go to multi-shot surveys, you're becoming latitude and inclination dependent in your errors for the azimuth. And again, they increase even more. So finally, to wrap up, what do we suggest for a decent survey? Okay, use an accurate north-seeking gyro tool, one which has high-frequency continuous data. So you're going to get as much possible data as you can, and then you want to use a final survey interval, depth interval, between surveys as small as possible. There's no reason you can't put thousands of surveys into a survey for a borehole. And calibrate the depth encoder carefully. It's very important. Depth is just as important as inclination and azimuth. And if you are drilling your borehole perpendicular to the formation, if you're lucky enough to get it to be, and minimize inclination and azimuth errors, you've still got depth errors to take into account. So when you've got your survey, do a pre and post survey roll test on the rig site and get a full survey QA/QC report from your supplier and verify the tool calibration. So you can use a calibration stand set up locally at your mine or in a nearby area. It's better than some of the options that people use of surveying with the tool into the same borehole every day as a calibration check. And that's it. Thank you very much, ladies and gentlemen.